Now, the formula we know can get very tedious, which is why I've been focusing on technology, and I encourage you to do the same. But there is a table in your book you can use as well. So the table works too. The only thing to keep in mind is that every value in the table is already pre-rounded to 3 decimal places. So if you wanted to be more accurate than 3 decimal places, you'd have to go into technology or do the formulas out by hand. But the tables can be nice for quick results when trying to find out these probabilities. Okay, so example 6. About 10% of workers ages 16 years and older in the United States commute to their jobs by carpooling. You randomly select 8 workers. What is the probability that exactly 4 of them carpool to work? Use a table to find the probability. Now, here, again, they haven't really defined what a success is, so you have to think about that interpretation. But it seems like a success in this case would be that it is someone who does carpool to work. So our N here is going to be 8 because we have 8 trials. And again, we're randomly selecting. So if we're randomly selecting, our trials should be independent. We're not going to be choosing people from like the same household or something like that, or same carpool, right? We're randomly selecting. So theoretically, they should be totally independent. Of course, it's always possible that you do grab 2 people from the same house or same carpool, but it's very rare. So we can assume independence here. Your probability of a success is 10%, so 0.10. And the probability of a failure then is 1 minus 0.10, which is 0.90. And we're looking for exactly 4 who carpool. So I want to know number of successes is 4 here. Now, you can use a formula, you can use technology. This is just another strategy you can use using a table. So the full table, this is just a piece of the table. The full table, it's table 2, is found in Appendix B of your text. So you can go back to that there. And what my goal here is to just quickly show you how to use it. So on the columns going down, you're going to see the p-value. So our p-value here is 0.10. So the first thing you need to find is your p-value. So you can see the book is highlighted for you so you can follow along. So here's our p-value of 0.10. Now, the other thing you need to find is it's going to be grouped by n's. So eventually, when you go down the page, you'll see the n equals 8 group, which is what we have here. And now within that group, we have 4 successes. So you're looking at 4. And if you match up the column with the row, you get a value of 0.005. So there's your probability, right? So what we're finding here, if you wanted to use technology, you could do the binomial PDF, and you'd have 8.10, 4, right? So specifically, I just need the value for 4. I don't need all values right now. And you're going to get about the same answer here. Now, again, all these values are rounded to 3 decimal places, so technology is definitely more accurate. And you can see, so they use Minitab here, another program. But you can see you do get that 0.005 when you round. But the drawback about the tables is, one, it doesn't have every single n value. So at some point it has to end, right? Where we don't want to take up hundreds of pages of different n values. And also, if you look at your probabilities, they tend to only go by 5s. So if our probability was 0.7, you don't have that exact value. Maybe you would take the average between the value for 0.05 and 0.10 to get an estimate, right? But you kind of start getting a little bit off track there. So the tables are really nice when your values actually match and can be found evenly. When they don't match perfectly well, so your probabilities get a little bit kind of weird or not as clear, then the tables aren't as helpful. But they are nice. So if you want something quick, and again, your probabilities are pretty simple, then the table can give you those probability values pretty quickly. The nice thing is here too, that if you go to your full n, you can get the full probability distribution right here as well, right? Again, assuming that your probability is in the chart. But all those values are right there for you, just like we got when we did it on a calculator. So just another strategy in case you want to check it out. And again, the full version is back in Appendix B in your text. All right. Because binomial distributions are discrete, probability distributions, we can graph the data using a frequency histogram here as well. So just like I mentioned in a few videos back, we can use frequency histograms here too, because binomials are still discrete probability distributions, so that the same rules hold. So let's look at an example. 62% of cancer survivors are ages 65 and older. You randomly select 6 cancer survivors and ask them whether they are 65 years of age or older. We're going to construct a probability distribution for the random variable x and then graph it. So here it looks like we're going to let a success be yes, they are 65 years or older. 62% of cancer survivors are in this age group, so our probability of a success is 0.62. Probability of failure is 1 minus this value, so 0.38. Let's see, we're selecting 6 people, so my n is 6 here, and I'm not going to specify the x, I'm going to do all the x's. And again, notice that we are meeting all the requirements here for binomial distribution. So we have our 2 answers, success or failure. We should have independence here. We're randomly selecting 6 people. That probability stays the same from trial to trial, and so on. The other thing you should be remembering is whenever we do these probability distributions, all of our probabilities are between 0 and 1, so that still holds, and the total still has to be 1. So we kind of haven't mentioned that here, but that still holds for this section too, because it's still a kind of discrete probability distribution. So those 2 pieces hold as well. Now, if I'm doing n equals 6, then my number of successes could be 0, 1, 2, 3, 4. Oops, I'm missing a row here. Sorry, 5 and 6. 1 short. There we go. Now, I'm going to, again, use technology here. If you want to do it out by hand, then feel free to go ahead and do that. But let's just use our technology. So I hit my second bars. I'm going down to my binomial PDF here. And let's see, my n is 6. My probability is 0.62. And then I'm not going to put an x in because I want it to do all of it for me. I'm just going to hit enter. Then I have all my values here. So your book uses 3 decimal places. I use the same. So 0.003, 0.029, 0.120. And then again, I can just click over and keep scrolling through the rest of them. I already have it done, so I'm just going to read off my notes here. 0.262, 0.320, 0.209, and then finally 0.057. And you can see I'm just taking all these values and rounding to 3 decimal places. 3 tends to be pretty common for probabilities. If it says something different, then do something different, but 3 tends to be very standard. So here's our probability distribution. And just like before, we can graph it. So you have all your options here for your x values, 0 through 6. Each of our widths are just a 1. So we're just doing a width of 1. And you just put your little numbers kind of at the midpoints where they would be. And then your heights here are your heights of your probabilities. So this one would be at 0.003, 0.003, 0.029, 0.120, 0.262, 0.320, and so on. So all those heights match. And just remember, like I mentioned before, is that as well, the area of each of these bars technically matches the probability as well, because the width is already 1. So when you have an area of a rectangle, you're just multiplying the length by the width. So your length here are those heights, your width is just 1. So we have this consistent idea that our probabilities and our areas are the same. Not that big of a deal here with discrete, but it's going to be a big deal next chapter on continuous. Now, one thing to note here, which is just good to remind us of, is from the histogram, and actually even from the table more clearly, we can see that it would be unusual for none or only one of the survivors to be 65 years or older, because both probabilities are less than 0.05. So remember, unless you're told otherwise, the most standard cutoff for unusual is 0.05. It can change in research, so it doesn't have to be 0.05. Sometimes we use 0.10 or 0.01, so there are variations. but usually 0.05 tends to be that main mark for unusual values. And if you look here in your probabilities above, you can see that these two here are very, very, very small. 6 is small too, but it's over the 0.05, but these two are less than. So if you were to choose 6 different people randomly, it would be very rare for you to have 0 survivors who are 65 or older, or only 1 survivor who are 65 or older. Be much more likely to have multiple survivors that are 65 or older based on our data. Okay, and then the last thing I want to talk about here is mean, variance, and standard deviation again. So like before, we had different formulas when we're dealing with tables. And actually, these formulas have been simplified for the binomial distributions. So there's still discrete probability distributions, but our formulas here can be simplified, really because we just have 2 outcomes. It makes it a little bit easier to actually find the mean, the variance, and the standard deviation. So when you have a binomial distribution specifically, we can use these formulas instead, which are pretty quick to use. So in Pittsburgh, Pennsylvania, about 56% of their days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June, and then interpret the results and determine unusual values. Now notice that we're focusing on the number of cloudy days. So I know it seems weird, but a success here is a cloudy day, right? Because that's what we're focusing on, for the number of cloudy days. So it may seem a little bit unusual to think of it that way, but that's what we have here. So our first thing is N. How many trials do we have? Now it's not very clear here how many times we're doing this, but notice that it's for the month of June. So how many days are in the month of June? Well, there's 30 days. So N here is 30 because we're looking at 30 days. Our P here is 0.56, right? Because that would be the probability of a success. And then our Q here is 1 minus 0.56, so 0.44. Now, we're not asking to find the probability for a specific number of successes. We're actually asked to find the mean, the variance, and standard deviation. So I don't need to find an exact X here, but I can go ahead and keep solving. So my mean is just N times P. My N is 30, my P is 0.56, and when I multiply these together, I get 16.8. So our mean is 16.8, so you would expect about 17 cloudy days in the month of June. So same notation for variance. I'm just using these formulas right here. So there's my mean formula, now my variance. It's going to be N times P times Q. So I have 30 times 0.56 times 0.44. And let's see, you get, I've rounded here, about 7.4. And then your standard deviation is the square root of that. Again, I would not just put the 7.4 in here because I rounded. So I would go back to that full value there, take the square root of it, and you get about 2.7. Now remember, these are all days, right? So variance is days squared, and then this is days. So on average, in June, Pittsburgh, Pennsylvania would have about 17 cloudy days. So looks like a little bit less than, so around 17 cloudy days. And a common standard deviation is 2.7, right? So if you went up 2 standard deviations and down 2 standard deviations, that'd be about 5 days. If you multiply this by 2, a little bit over. So in either direction, that would still be usual here. So let's actually do that out. So let's do our mean plus our 2 standard deviations. So we have 16.8 plus 2 times 2.7. And again, it's a little bit more than 5. So when we add everything together, we get 22.2. And if we do our mean minus 2 standard deviations, we get 11.4. So remember, for standard deviation, anything in between 11.4 and 22.2 is considered usual. So if you have between 11.4 and 22.2 cloudy days in the month of June, this would be considered totally normal. Anything beyond that is unusual. So if you are beyond this, now you're starting to have unusual weather, or if you're beyond it this way, you're starting to have unusual weather. Now, watch your decimals here. So you do want to actually include those decimals. It may seem a little bit weird, but for instance, if we're thinking about full days, then our usual full days would actually be 12 days to 22 days, right? Because you can't have 11 and a half days, really. I mean, I guess you could, but really we talk about a full day, right? So 12 days cloudy to 22 days cloudy would be normal. Those are both inside these ranges. After 22.2, the next day is 23. So anything from 23 to 30 days is going to be unusual. And then going this way, 11 would be included. So anything from 0 to 11 days would also be considered unusual. So if you had 23 or more cloudy days, that would be unusual. Or if you had 11 or less cloudy days, that would also be unusual. Okay, so we still have that same idea of about that 2 standard deviation cutoff, right, as being unusual here.